this session, we're going to take a short look at a very important part of a Six Sigma program. For this course, we want you to understand the importance of a measurement system analysis and the key properties of good equipment, and to give you some guidelines for assessing the quality of a measurement system. However, we're not going to be able to focus on the calculations, as these types of analyses can be very long and are generally done in a statistical package. So what we've done instead is provide you some definitions and examples in this section and the next section to give you a feel for the requirements of an MSA study. We've also asked for a contribution from the American Society of Quality from Mr. Zubair Anwar, and he will give us a full example of a gauge R&R study. We also want to mention that this is just an introduction and a few guidelines. To set up an MSA for a particular case at your work, you should use this as an initial reference only. The learning objectives are to be able to understand the purpose of a measurement system analysis, to define the properties of a measurement system, bias, precision, stability, linearity, and resolution, to describe the properties of a good instrument, and to list the evaluations used in a gauge R&R study. The measurement system analysis, or MSA, is done to make sure that the measuring instruments of adequate capability are available for taking measurements on the product characteristics and product variables and process variables of a given process, and that the measuring instruments will measure these characteristics and variables truthfully. When we say measurement system, we're implying that there's a scheme or system existing, including instruments, equipment, operators, software, procedures, everything that is required to produce a measurement. Also, the main reference for this section is Measurement System Analysis, MSA, Reference Manual, which is published by the three big automakers, Chrysler, Ford, and General Motors, and is also available online. So why is MSA important in Six Sigma? Six Sigma is a data-driven methodology, which means that data measurements are the foundation for our decisions. From defining the problem, where we take measurements to establish the baseline process performance for our critical to quality parameter, the process capability. In measure, we look at influencing parameters and decide on which data to collect and how, including defining our sampling plan. In analyze, measurements are needed to see if a significant relationships exist between two or more parameters, how process parameters influence the output parameters, and we then continue this and improve to see what we can change in our process to improve the results. And finally, in control, we also use measurements to control the process. We calculate a statistic from sample data, and we compare this with statistical control limits for the process. And if the comparison indicates that the process is out of statistical control, then an adjustment of some kind is made. This means that the quality of the data is paramount. Poor quality data will lead to poor results in every part of the DMAIC cycle and will not yield any benefits. When do we use a measurement systems analysis? Well, you do this before you collect any data from your process. For example, if you want to analyze the process capability, you use the measurement system analysis to confirm that the measurement system measures consistently and accurately and adequately discriminates between the parts. First, we need to go through some definitions, though. These you are responsible for. Gauge is any device used to obtain measurements, frequently used to refer specifically to the devices used on the shop floor. Measurement system, as we just said, is the complete process used to obtain measurements. It's the collection of instruments, or as we just said, gauges, operators, standards, methods, software, personnel, environment, and various assumptions that we've made, everything that's used to produce a measurement. Standard is a known or reference value, known within given limits of uncertainty and accepted as a true value. The standard should be an operational definition, a definition which will yield the same results when applied either by the supplier or the customer without changing over time. The standards for characteristics such as length or weight or hardness or color or so on are maintained by standard organizations of individual nations, and these are called national standards. For the United States, for example, the national standards are maintained by NIST, the National Institute of Standards and Technology, which is in Gaithersburg, Maryland. And every industrial nation has a national standard organization of its own, which maintains the national standards for that country and regularly exchanges with other countries. Now, let's go through this graph together. We want to understand what we mean by measurement error or measurement variation. So we've seen the variability in measured data is quantified using standard deviation of the distribution of the readings. This is often referred to as error standard deviation or just simply the error. So when we have a measured value, that measured value is comprised of the true value plus any observed variation or observed error. Now this observed variation, or we could call it the measured process variability, can come from true variability. So we have the true long-term and short-term process variation, which is inherent in any process. But it can also, the observed variation can also stem from measurement errors or measurement variation. So therefore, the observed variation comes from true variation or inherent process variability and error variation. This error variation then, or measurement variation, can be due to several reasons. For example, sample variation or errors in sampling can also be due to finding out that the measurement that you're trying to make is not really valid for the goal you're trying to achieve. And what we're going to focus on is here the measurement reliability. This is an important part of the MSA. The reliability of measurement data is defined by statistical properties of multiple measurements obtained from the measurement system operating on stable conditions. So in other words, with no experiment going on, we take multiple measurements using our measurement system, and then we evaluate the statistical properties and see if indeed the measurement reliability is small. So in order to evaluate this measurement reliability, we need to define several important measurements. Every instrument, be it a caliper or a micrometer or thermometer, every instrument produces the measurement with a certain variability. In other words, if an instrument is used to measure the same characteristic on the same unit of a product repeatedly, there should be no change in the value. But due to this variability of the instrument, the results from all the trials will not be exactly the same. This variability in the readings can be described by a distribution, normally the normal distribution. And the average of the distribution can then be used as the measurement provided by the measuring scheme. The difference between this average and the true value of the measurement is called a bias. The accuracy of an instrument, of course, is the opposite then of bias. The smaller the bias, the better the accuracy. We look at a picture at this in a minute. So an instrument that provides measurements with a smaller bias is more accurate. Now, as we just said on the previous slide, the variability in the readings is quantified using the standard deviation of the distribution of the readings, or the error. The precision of an instrument is the opposite of this variability. The smaller the variability in the readings, the higher the precision of the instrument. And the sources of variability come from repeatability. This assesses whether the same appraiser can measure the same part or sample multiple times with the same measurement device and get the same value. Reproducibility assesses whether the different appraisers, by appraiser I mean operator or the people doing the measurements. So reproducibility assesses whether different appraisers can measure the same part or sample with the same measurement device and always get the same value. And here we see some pictures of this. So again, bias is the difference between the average of the readings and the true value of the measurement. And so here we can see, in this case, we have our measurement value here on the x-axis, and there's a distribution, and we have a mean value, which differs from the true value here. And the difference between these two is the bias. So here we have, in this case, a large bias. In this case, for example, a small bias. Precision, we said, was measured by the standard deviation of the readings, which measures the lack of precision, or the opposite of variability. So here, for example, we have a large standard deviation. Here we have a smaller standard deviation. So here we have a large variability, and here we have a small variability. So here, in this case, we have a low precision, and here we have a high precision. And the same in the bottom case. In this case, we have a small bias, but here we have a low precision. The measurements, which should all be exactly the same, are widely varied, and here we have, again, a high precision. And also here, a small bias. So the difference, again, the difference in the bias is the difference from your average value that you get from the true value. So clearly what you're looking for then is a small bias with a small variability or high precision. And here we have the pictures again of the bullseye, different definition of bias and precision. The same as in the slide before. Here we have the sharpshooter shooting not only off target, but slightly wildly. So you have it's not accurate and not precise. Here he's shooting rather wildly, but at least around the target. So he's fairly accurate, but not precise. Here we've got, he's very precise. He's always able to shoot in almost the same spot, but he's way off the bullseye there, so he's not very accurate. So low bias. And here we have finally high bias. I can't circle in red. High bias. Whoops. Whoops. High bias and high precision for this last one. Change my pen here. So maybe that gives you maybe an easier way to think about what these ideas of bias and precision made. So a few more definitions. We also have two other properties of instruments, linearity and stability. Linearity refers to how the bias remains the same over the range of possible values of the measurement, whereas stability refers to how the precision of an instrument remains consistent over time. So here we have again some pictures of stability and linearity. So here what we see is that we have no linearity problem here. The bias remains the same over all different values of the range of values that we're measuring. So if it were temperature, low temperature, and high temperature, the bias remains the same. Here we have the opposite case. The bias starts as a small bias, and then it gets larger for higher values. So we have a linearity problem in the second example. In the bottom, we're looking at the change in time. So this is our stability concept. As time goes on, you can see here, we have no change in precision over time. The variability of our data is approximately the same as we move on in time. Whereas in this bottom picture, now this is a stable system, whereas in the bottom picture, we see first we have a small variation and we have a large variation, so we have an unstable system. The precision changes over time. Finally, we have resolution. This refers to the smallest division of the unit that the instrument is designed to measure. For example, it's the smallest division on a foot rule is 1/16 of an inch, then this is the resolution of the foot rule. If you're working in Germany and you're using the metric system and you're using, for example, a meter, then maybe your smallest, your resolution might be a millimeter, for example. So going back to our chart, to summarize, the measured value is going to be equal to the true value plus some kind of observed variation. This observed variation that is made up of true variation, process variation, and then variation due to the measurement. This can be due to errors, sampling variation, for example. It can be due to the fact that you have your measurement is not really valid, and it can be due then to reliability problems in your measurement. The reliability then is defined by the statistical properties of these multiple measurements on the measurement system under stable conditions, and the ones that are most commonly used to characterize, as we've just learned, are bias, referring to the location of the data. Write this down, location of data, relative to a reference or a standard value. And again, bias is the deviation between the measurement and the true value, while precision refers to the spread of the data. Good measurements, then, should have the following properties, good measurement systems. They should have very low bias, so near zero bias, which means that the difference between the measurement and its true value should be very close. They should have adequate resolution suitable for the purpose that the instrument is being used for. They should have stability, which refers to how the precision of the instrument remains constant with time. And they should not have any linearity problems, which refers to how the bias remains the same over the range of possible values for the measurement. They should also have high precision. So a good measurement system should have high precision. And this is generally measured, as we said, by repeatability and reproducibility, where we have repeatability is due to the equipment, due to the gauge, and reproducibility is any variation due to the operators. And then once again, a measurement system analysis is done to make sure that the measuring instruments of adequate capability are there, that you can take your measurements truthfully, and just again, the specific procedures for an MSA would have to be modified to suit your specific case. And there may be some special circumstances, so this is just a guide. A good instrument then, to summarize, should have good resolution, near zero bias, measurement variability much smaller than the variability in the product it's used to measure, variability that is small compared to the tolerance allowed in the product, stability and precision, and no linearity problem. The true variation between outputs should be larger than the error variation of the measurement system. And these sources of variation can be estimated with what we call a gauge R and R study. The Measurement System Analysis Reference Manual recommends that before starting to test the acceptability of an instrument. The question of whether the measurement in question is needed at all should be considered. So one step back from everything we just said, do you even need the measurement? There are many measurements being taken in production shops that serve no particular useful purpose, and there's no need for elaborate checking of the instruments and an MSA for the measurement if it's not needed. So it is important at first to check how the results from the measurement are used and their usefulness in determining the condition of a process or the acceptability of a product. Also, a preliminary evaluation should be made whether or not the instrument in question is affected by the environment in which the measurement is taken. This can be things like ambient temperature, can be often humidity or even lighting that could affect the measurement, as well as, for example, maybe you have some kind of accumulation of gas or something else. These are some of the factors that often affect the measuring process without people realizing. If any such factors seem to influence the measurement, then there need to be further experiments to evaluate the instrument, taking these factors into consideration. So the property of an instrument to be evaluated in a so-called gauge R&R study are the resolution, the bias, the variability from repeatability and reproducibility, stability and linearity. And these are collectively often called a gauge R&R study, the R&R, of course, refers to this reproducibility and repeatability, which are often a major part of the study. And so generally, when we say gauge R&R, we're referring to the entire collection of tests.